In the heart of the 17th century, as Europe emerged from the intellectual slumber of the Middle Ages, a scientific revolution was brewing. This was a time of great change, where the old ways of thinking were being challenged by new ideas and discoveries. This revolution, fueled by curiosity, observation, and reason, would forever change our understanding of the universe and our place within it. It was a period where the thirst for knowledge was insatiable, and the pursuit of truth was relentless. At the forefront of this revolution stood a towering figure, a man whose genius would illuminate the world and lay the foundation for modern science, Sir Isaac Newton. His contributions would become the cornerstone of physics and mathematics. Born in 1643 in Woolsthorpe, England, Newton was a child of the countryside. His early life was marked by the simplicity and tranquility of rural England, a stark contrast to the bustling cities where many of his contemporaries lived. He grew up in a world where superstition and tradition often overshadowed reason and observation. The beliefs of the time were deeply rooted in folklore and religious doctrine, leaving little room for scientific inquiry. Yet, from a young age, Newton displayed an insatiable curiosity about the world around him. He built intricate models, demonstrating a keen understanding of mechanics and an innovative spirit that set him apart from his peers. He observed the motions of the stars, fascinated by the celestial bodies that adorned the night sky. His observations were meticulous, laying the groundwork for his future astronomical studies, and devoured every book he could find on mathematics and natural philosophy. His hunger for knowledge was unquenchable, and he spent countless hours immersed in the works of the great minds that preceded him. This thirst for knowledge would lead him to Trinity College, Cambridge, a place renowned for its academic excellence. Here, Newton found an environment that nurtured his intellectual pursuits and provided him with the resources to explore his ideas, where he immersed himself in the works of the great thinkers who came before him, Euclid, Galileo, Kepler, and Descartes. These scholars laid the foundation upon which Newton would build his revolutionary theories. But Newton was not content to simply absorb the knowledge of the past. He yearned to push beyond the boundaries of the known, to challenge the established norms and seek out new truths, to explore the mysteries of the universe with fresh eyes and a mind unconstrained by dogma. His experiments with light and prisms, for instance, revealed the nature of color and light, fundamentally altering our understanding of optics. Little did he know that his journey would lead to discoveries that would reshape our understanding of the cosmos and redefine the limits of human intellect. His magnum opus, the Principia Mathematica, would become one of the most important works in the history of science, laying down the laws of motion and universal gravitation. In the realm of physics, Newton's contributions are unparalleled. His work has fundamentally shaped our understanding of the physical world and continues to influence modern science. His three laws of motion, first presented in his masterpiece, the Philosophiae Naturalis Principia Mathematica in 1687, form the bedrock of classical mechanics. This monumental work not only introduced these laws but also laid the foundation for the field of physics as we know it today. These laws, elegant in their simplicity yet profound in their implications, provide a comprehensive framework for understanding the motion of objects. They have been tested and validated countless times, proving their accuracy and reliability in describing physical phenomena. The first law, often called the law of inertia, states that an object at rest will stay at rest, and an object in motion will stay in motion at the same speed and in the same direction unless acted upon by an unbalanced force. This principle is fundamental to our understanding of motion and stability. Imagine a ball rolling on a frictionless surface. It will continue rolling in a straight line forever unless something like friction or a wall stops it. This concept is crucial in explaining why objects behave the way they do in different environments. The second law delves into the relationship between force, mass, and acceleration. It provides a quantitative description of the changes that a force can produce in the motion of an object. It states that the force acting on an object is equal to its mass times its acceleration, F equals sine of ma. This equation is a cornerstone of classical mechanics, allowing us to predict how objects will move under various forces. This means that a heavier object will require more force to accelerate it at the same rate as a lighter object. This principle is evident in everyday experiences and is essential for engineering and technology. For instance, pushing a car requires more force than pushing a bicycle. This simple observation is a direct application of Newton's second law and helps us understand the mechanics of different objects. The third law, perhaps the most well-known, states that for every action there is an equal and opposite reaction. This law is fundamental to the interactions between objects and forces. When you jump on a trampoline, you exert a downward force on it. This action is met with an equal and opposite reaction from the trampoline. In return, the trampoline exerts an equal force upwards, propelling you into the air. This interaction is a perfect demonstration of Newton's third law in action. These three laws, intertwined and interdependent, laid the groundwork for understanding everything from the trajectory of a cannonball to the orbits of planets. They have been instrumental in the development of various fields, including astronomy, engineering, and even space exploration. Newton's laws of motion are not just historical artifacts, they are living principles that continue to guide scientific inquiry and technological advancement. From the simplest machines to the most complex spacecraft, these laws are at the heart of our quest to understand and manipulate the physical world. As we venture further into space and explore new frontiers, Newton's insights remain as relevant as ever. They remind us of the power of human curiosity and the enduring quest for knowledge that drives scientific progress. In honoring Newton's legacy, we celebrate the spirit of discovery and the profound impact that one individual's work can have on the world. His laws of motion are a testament to the enduring power of scientific thought and the limitless potential of human ingenuity. Newton's genius was not confined to the terrestrial realm. It extended to the celestial sphere, unraveling one of the universe's most fundamental forces, gravity. His work laid the foundation for modern physics and astronomy, bridging the gap between the observable world and the vast cosmos. Legend has it that Newton's epiphany came as he sat beneath an apple tree observing the fall of an apple. This simple yet profound moment is often romanticized, but it was Newton's unparalleled curiosity and intellect that transformed this everyday occurrence into a groundbreaking scientific revelation. This seemingly mundane event sparked a profound question in his mind. If an apple falls to the earth, could the same force that pulls the apple also be responsible for keeping the moon in its orbit around our planet? Newton pondered the connection between the falling apple and the celestial bodies, leading him to explore the nature of gravitational forces. From this simple observation, Newton developed his law of universal gravitation. He meticulously documented his findings, combining mathematical rigor with empirical observations, which culminated in his seminal work, the Principia Mathematica. This law states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This elegant equation not only explained the motion of planets but also provided insights into the behavior of objects on Earth. In simpler terms, objects with more mass exert a stronger gravitational pull, and the force of gravity weakens as objects get farther apart. This principle is fundamental to our understanding of the universe, influencing everything from the formation of galaxies to the trajectory of a thrown ball. This groundbreaking concept explained why the moon orbits the Earth, why the Earth and other planets orbit the sun, and why tides rise and fall. Newton's insights provided a coherent explanation for the motion of celestial bodies, unifying the heavens and the earth under a single, universal law. It provided a unifying framework for understanding the intricate dance of celestial objects, demonstrating that the same laws of physics govern both the heavens and the earth. Newton's work not only revolutionized science but also inspired generations of thinkers to explore the mysteries of the universe, forever changing our perception of the cosmos. Section 4, Calculus, a new language for the universe. Newton's quest to understand the universe's workings led him to invent a new mathematical language, calculus. While the seeds of calculus were already present in the works of ancient Greek mathematicians and later explored by thinkers like Pierre de Fermat, It was Newton who independently developed a comprehensive system of calculus. He recognized the limitations of traditional geometry and algebra in describing the continuous change and motion he observed in the natural world. Calculus provided the tools to analyze these complex phenomena, offering a way to quantify instantaneous rates of change, such as the velocity and acceleration of a falling object or the slope of a curve at a specific point. It's like having a speedometer that not only tells you your current speed, but also how quickly your speed is changing. Newton's calculus revolutionized mathematics and physics, providing a powerful framework for describing everything from the motion of fluids to the behavior of light. Its applications extended far beyond the realm of physics, influencing fields like engineering, economics, and computer science. Section 5: Optics: Unlocking the Secrets of Light. Beyond the realms of motion and gravity, Newton delved into the enigmatic nature of light, conducting groundbreaking experiments that challenged prevailing theories. In a darkened room, he passed a beam of sunlight through a glass prism, witnessing the separation of white light into its constituent colors, a phenomenon we now call a spectrum. This experiment, simple yet profound, demonstrated that white light is not a single entity but a composite of different colors, each with its own unique wavelength. This revelation overturned the long-held belief that color was a property of objects rather than light itself. Newton's work in optics extended far beyond the prism experiment. He explored the phenomena of refraction, reflection, and diffraction, developing theories to explain how light interacts with matter. His groundbreaking book, Optics, published in 1704, laid the foundation for the science of optics and revolutionized our understanding of the nature of light.